Okay, so for problem number 1, part A, we're looking at a spherical volume that is charged uniformly. What that tells us is that this is an insulator, because if it has charges within the volume, then it can't be a conductor, because conductors will move all those charges to the surface. So in this scenario, when we're working outside of the sphere, it's pretty easy, and you can use Gauss's law, but hopefully up to this point you've realized that for any charged spheres, if we're working or looking at the electric field on the outside of those charged spheres, then we can use the equation for the electric field of a point charge, which is kq over r squared. And then we just need to make sure that in relating this to Gauss's law, that this is our Q enclosed. So anytime we are outside of a charged sphere, whether it's an insulator or conductor, we can use this equation. And I'm going to substitute my Q enclosed, which is the full charge of this sphere. And then R, this is my arbitrary radius of my Gaussian surface, is going to be lowercase r, not uppercase r, and you have to make sure to distinguish between those two. A lot of students just plug in big R and little r interchangeably, and that's not okay. So here's the harder part. When we are working within our sphere, so I'm going to make a Q enclosed inside. My charge enclosed is a little bit harder to work with. Now normally, well, first we're always going to think about rho, which again, you want to memorize this because it's not in your equation sheet. It's dq over d volume. And if my rho was not a constant, they gave me an equation, so it's not uniformly distributed, it is actually ununiform, then I would have to use calculus. If rho was some expression with respect to r. Now, in this scenario, it is uniform. So what we know is that if I just took this Q enclosed here and I put it over the volume enclosed of that sphere, then it would be equal to the density of the full charge over the full volume. Now, we are going to use Gauss's law, so I should always start with my fundamental principle, but I'm going to solve for Q enclosed first. So here is my volume equation for a sphere, 4/3 pi r cubed, and it's going to be little r because remember I'm focused on the volume enclosed, which is an arbitrary little r value, and then the big Q over the full volume is going to be the same equation except big R cubed, which is the volume of the entire sphere encompassing the entire charge Q. From there we simplify and we get that Q enclosed is equal to Q over little r cubed over big R cubed. And we actually did this many times when we were working with an object falling through the center of the earth and trying to find the gravitational field of, or the gravitational acceleration value for an object falling through the center of the earth. Okay, so I've got dq. I need to plug in the rest of my equation for Gauss's law, so I'm going to continue here, which my electric field dot dA, if I do my enclosed integral, which is integrating along the entire surface of that sphere, I get the equation for the surface of a sphere. And it is always going to be, this dA is always going to be the Gaussian surface. So always little r. And then on the right side, I'm plugging in my Q enclosed, and then I can't forget my epsilon naught. And then your electric field is going to be QR over the 4 pi epsilon naught is K. So I'm going to bring that out in front. 1 over 4 pi epsilon naught is K. And then I've got my R cubed in the denominator. So this is my electric field within the insulator, and this is my electric field outside. All right, next step is to find the potential. So the equation to find the potential, now that we have these electric fields, is to do the change in potential is equal to the negative electric field dr. So we always want to start at infinity. That's where my distance is equal to 0. So I'm going to go from infinity to the surface, and I am going to, just to save room, I am going to, actually never mind, I am going to pull out my constants. So this is my electric field equation, KQ, and I'm going to integrate from infinity to R, R to the negative 2 dr. My variable is in the denominator, the r squared, and so I turn it into a negative 1 power to make it a polynomial. One thing before I start this integration is delta V is V final minus V initial. And I already know that V initial is equal to 0, so I can cancel out. And now let me finish off this integral. This is negative 1 over r, which goes from infinity to r. The negatives end up turning into positives. And I know that when I do the difference of my upper minus my lower limit, the 1 over infinity is going to turn into 0. So when I plug this in, I have KQ over R. And that's exactly what we expected. Again, when you're working with a sphere, you can, and you're trying to find the potential or the electric field outside of that sphere, whether it's a conductor and an insulator, your potential and your electric field are going to be the potential and electric field equation for a point charge. So KQ over R and KQ over R squared. And then obviously we're at the surface, so I'm using big R as my denominator. The next part is finding the potential at the center of the sphere. Now, if this sphere was a conductor, then my potential would be equal to this guy, the potential on the surface. Why? Because the electric field is equal to 0 at the center of a conductor, and therefore the change in potential is equal to 0 and therefore constant. So we went over that many, many times in class. This is a new scenario where we don't have a conductive sphere. And so we're going to just do the same process. There's nothing new. I'm doing delta V. I'm going from the outside of the sphere to the center of the sphere. So it's going to be from V final is V naught minus VR. And then I have to do my negative integral. And this time, the electric field in that region is going to be my equation KQR over R cubed. So I've got a lot of constants here that I want to pull out. And my limits are going to go from R to 0. And this time, my variable is R. So when I integrate R, I'm going to get negative KQ over big R cubed, R, little r squared over 2, and then I go from 0 to R. Now, I have to keep in mind I'm not solving for the change in potential, I'm solving for V naught. So I am going to plug in my equation for VR, because I know I'm going to have to add that to the other side later. But let's simplify this right side. This is equal to negative KQ over 2R cubed from 0 squared minus big R squared. If I simplify that out, I get a positive KQ over 2R. And then when I add this guy to the other side, plus KQ over R, I get a V naught, which is equal to 3 KQ over 2R. And that is your final answer.